All right, for the second part of this problem, we're going to take this same satellite and try to give it the same orbital radius, but we know that Venus has a smaller mass, so think about it. If we think about it, if we have the same radius but a smaller mass, centralized mass, then it seems that we would have a smaller speed. So we'll check that out and see if the answer that we get is consistent with that sort of intuitive sense of what must be going on here. All right, so we do have to go back and use the orbital radius that we got before. So we're going to say the orbital radius, 1.1 times 10 to the 7th meters. We are going to have to kind of Texas two-step that one, but we'll just plug that in when it comes time. All right, so we have a mass that's approximately 80% that of Earth. How fast does half to travel? This is an interesting application of the idea we talked about just a few minutes ago, and that is the idea of getting all the constants on one side and all the variables on the other. As with many of these situations, we're going to get that the centripetal force is just gravitational force. So since we know those are equal, we'll find our same expressions. Since we're going to be dealing with speed here, how fast, we're going to be dealing with velocity. So we're going to say the centripetal force here, mv squared over r, is equal to the gravitational force, which in this case, again, will be g central mass, in this case mass of Venus, times the mass of the satellite divided by the orbital radius squared. All right, in this situation, again, it's going to be easy to get rid of a couple things. Snow day at the Vatican. And we'll get rid of one of the r's here, multiply through by r. And as before, we end up with v squared is equal to gm over r. Now, in this case, this is a little bit unusual because actually, most of the time, we have mass, this big mass, stays constant. But in this particular problem, it's the radius that's staying constant. And this mass, we're changing from Earth's mass in case 1 to Venus's mass in case 2. So our equation with all the variables on one side and all of the constants on the other side is going to be rearranged a little bit. And what we'll see now is v squared over m is equal to g over r. All right, so how does that work for us? This is, on this side, these are our variables. On this side, these are constant. Okay, so v squared over m is going to change from Earth to, well, actually, since this stays the same, then v squared around Earth divided by Earth's mass is going to be equal to v squared around Venus divided by Venus's mass. Okay? Since they're both equal to g over r, constant, right? Because we're given that the radius is constant. All right? So those two things, since they're both equal to the same thing, will be equal to each other. All right, so we will take all of this right here. We'll take this expression and just borrow it, bring it down here, and then we'll just solve from here. So going from here, solving for the velocity around Venus, all we have to do is multiply each side by m over v, or m sub v, the mass of Venus, and we will end up with velocity around Venus squared is equal to mv over me times ve squared. Okay? So the inverse ratio of their masses. All right, so that gives us that VV, velocity around Venus, is going to be equal to velocity around Earth times the square root of mv over me. Now again, because I gave the mass of Venus in terms of the mass of Earth, it makes things a little bit simpler. We could say VV is equal to velocity around Earth times the square root of 0.8 Earth masses divided by the mass of Earth, right? Because this right here is the mass of Venus. ME cancels out, and we're going to get velocity around Venus is equal to velocity around Earth times the square root of 0.8. And you can see that there's no dimensional considerations here. It makes things very easy. So given that the velocity around Earth was 6,000 meters per second, and that was given, we have VV is equal to 6,000 meters per second times the square root of 0.8. And that's going to turn out velocity around Venus, 5367 meters per second, but we would give that as 5,400 meters per second, and that was what one of your answer choices was on the multiple choice quiz that we took.